All right. So, as I told you, today we will continue now with Josephson junction. And we will actually deal with the realistic Josephson junction, not the idealized Josephson junction that we have been dealing with so far. Now, when I tell you about Josephson junction, one of the things that I want to emphasize now that we have derived the Josephson junction for a weak link, two large superconducting pads connected through a narrow channel like this. However, you have to remember that this is not the only way you can realize a Josephson junction. This is one of the way to realize a Josephson junction, and this is called as weak link Josephson junction. But there are also other kinds of Josephson junction, and the most popular one is actually a tunnel junction. So you have a superconductor 1, a very narrow insulating barrier, and a superconductor 2. So here this is not a link that's physically like this, but you can show that exactly the same phenomena would happen if you have a thin Josephson junction. Sorry, a thin tunnel junction. So you will get, here again you will get the Josephson junction.
Sir, I can't understand what you have said just. What is not physical?
Yeah, just a minute. Just a minute. There is a problem with the one note. Yeah, what are you asking? What's the question?
Yeah, you have said that these one insulator to the structure is not the ideal. It's not in one insulator two. That's not the physical thing. Rather, the diode structure is the tunnel junction. Yeah, the tunnel diode structure is the physical thing. Uh, but how these two are analogous?
No. Where is this? Where do you get the diode? I have no diode anywhere. Did I mention diode? These are superconductors. Diodes normally is when I have a P and a N junction of two semiconductors. Where did you get a diode here?
Okay, okay.
No, what is the question? Maybe I am not understanding what you are
Yeah,
saying.
yeah. You have told something about one thing is physical and one thing is analogous to that.
No. Both are physical. There is nothing unphysical in anything here. One of them is you have two superconductors, 1 and 2, separated by a weak link. The way we have defined a weak link is the narrow channel whose dimension is much smaller than the coherence length and the penetration depth. The other realization of a Josephson junction is two superconductors. They are again they need to come into contact with each other so that you can have exchange of Cooper pairs. But here, instead of connecting them through a weak link, you are connecting them through a tunnel barrier. That also will produce a Josephson junction, because you can have, let's say, a Cooper pair here that will tunnel as a Cooper pair on the other side. Okay, that will also give you exactly the same Josephson junction phenomena that we have derived, which is that the supercurrent
So
will be
why we
proportional.
should so then why we should put the insulator in between two superconductors to have the tunneling?
Because you need a weak, you need these two superconductors to be connected but weakly connected. If you connect them very strongly, then it becomes one superconductor.
Okay, okay.
Okay.
So
Then
here
what
the action of weak link is played by the insulator.
the weak link is what the weak, yeah, the action of the weak link is played by the insulator. What the weak link does is that at the contact between the two superconductors, the order parameter gets suppressed. That is actually
Yeah,
the role of the
yeah,
weak link here.
yeah. Okay.
Get not completely suppressed, partially suppressed. If you completely suppress, then of course there will be no exchange of anything.
Yeah,
All
yes,
right.
got the point. Yeah,
Hmm? Yes.
got the point, sir. Thank you.
All right. So now, however, any real Josephson junction, whether it is like this or whether it is like this, will have two other ingredients. So first, let me show the idealized Josephson junction. Remember, you know that in a circuit, the convention is that if you have a resistor, then you show a resistor like this. This is a convention of a resistor. A capacitor is like this. An inductor is often like this. So, similarly, the notation for a Josephson junction is a cross. This is an ideal Josephson junction. However, if you have two metals like this, which are so close to each other, or here two metals like this, so metals I mean conducting electrode, superconductor is also a conductor, which are so close to each other, there will be a capacitance. You need to necessarily have a capacitance between the plate. So therefore, any realistic Josephson junction will have a parallel capacitance. Now that is not all. You will also always have a resistance in the junction. The resistance in the junction will of course come into play only when you apply a current which is larger than the critical current. If you are lower than the critical current, then the resistance does not come into play. And where does the resistance physically come from? You know that the resistance R in the normal state is Rn, and then when you are cooling down, you are gradually increasing the superfluid density. You have a fraction of super electron and normal electron. Okay? So therefore, so this is the resistive part, and as I cool, I will have this parallel resistance that will roughly drop off exponentially. Okay, so I have a resistor here. Now again remember, if I am now passing a current that is smaller than the critical current of this junction, then the whole current will pass through this. The current has no reason, and if it is a DC current, it has no reason to pass through the resistor. But if I pass a current which is larger than the critical current, then I will have a voltage. So then part of the current will go through my Josephson junction and part of it through the resistor, because I also have normal electron in the weak link. So this follows essentially from the fact that in the weak link I have both normal electron as well as super electron. So this entity that I have drawn here is now a realistic Josephson junction, and this has a name. This is called resistive, so RCSJ. If you give a search, you'll find RCSJ model in many places. This means resistance, capacitance, shunted Josephson junction. So this RCSJ is the any Josephson junction is actually always a RCSJ. This resistance, if you are at very low temperature, this resistance is very, very large, and therefore it does not contribute at all, because you don't have normal electron at low temperature. For a clean superconductor, the normal electron becomes very small. So therefore this resistance becomes very, very large. And since the resistance is large, it really can disappear. But at finite temperature, this resistance is always there. And this capacitance, of course, you cannot get rid of. It depends on the geometry and how you have produced the Josephson junction. So now we will work with the RCSJ model, and we'll see that the RCSJ model gives us some very, very nice things. Okay, so let us try to set up the RCSJ model. So now if I pass a current, the most general situation is that the current, part of it will pass through the Josephson junction, that I call it the supercurrent. Then part of the current will pass through the capacitor. Of course, the DC current will not pass through the capacitor, but this is the general expression. I am not assuming anything about DC or AC. It's just the general expression. And part of the current will pass through the resistor. So you have three channels. So you know that IS will be given by IC sine of gamma, where gamma is the gauge invariant phase. This was part of your assignment problem that you have already submitted. So therefore, the first term is IC sine gamma. What is the second term? Now you know that the current through a capacitor is proportional to the rate of change of voltage. So it is C dV/dt. And the current through a resistor is given by Ohm's law. So it is V by R. Now I also know that the voltage is given by the second Josephson relation. This is the rate of change of the gauge invariant phase. So therefore, now I can write the full equation in terms of the gauge invariant phase only. And that is going to give me a second order differential equation. Good. So this is a second order differential equation under various limits. You can reduce it to the equation of a damped forced harmonic oscillator. So let us write it in a slightly different form. Okay, so if I write this term as 1 by q d omega dt, I define, so I told you this is I can map it to a harmonic oscillator with damping. So the characteristic frequency of that harmonic oscillator will be given by the plasma frequency. This is called the Josephson plasma frequency. So it is twice EIC by CH cross to the power half. Okay, and then you can actually write this Q as much more in a much more elegant way. Just give me a minute. Subrato, I'm taking a class. I will call you later. Okay, so I can write this as omega p RC, and then if I do a variable transformation instead of t, if I change my variable to this dimensionless time, which is omega p into t, then I can have the Josephson equation which becomes universal. So this is quite a nice thing, because if I have a universal equation, I can always solve this one equation, and then for different Josephson junction, I just have to back transform by going to the non-universal parameter, non-normalized to the dimensional parameters. Okay, this is the Josephson junction equation based on the generalized type. But now let us go back and see what's the solution of this equation, because that's from where the fun starts. Okay. So what I will be showing you now, and this is really interesting, that this equation, the Josephson junction problem, I can transform and map it to a problem of classical mechanics. And the problem of classical mechanics that I will transform into is what we know as the tilted washboard model. Okay, so washboard is, I think, a little bit of a Western concept. So let me explain what the tilted washboard model is. A washboard is actually a board on which you sort of you take your clothes, and you, when washing your clothes, you hit with the washboard on the cloth. So the washboard has a surface which is roughly like this. So when you hit the cloth with the washboard or the cloth on the washboard, that's the way you clean it. That's the way all hobbies clean their things. But I think in India they normally take the cloth and hit it on a stone instead of a washboard. Okay, so you have this washboard here. Now, a tilted washboard is an idealized mathematical tilted washboard is that you have a sinusoidal undulation on the surface. Now you put a ball here, and this surface, now you tilt it, and you look at the dynamics of this ball. So this ball initially will be nice inside that potential well, and then at some point it will get out of the well and it will start rolling. And then you can put a bit of molten chocolate on this washboard and you'll have viscosity. So then you have a ball rolling down on a potential that has this sinusoidal uh, modulation, and it also has uh, viscosity inbuilt. So what I will show you is that this mechanical problem, this classical mechanics problem, maps directly on this. So therefore, these quantum mechanical phenomena, you know, to understand it, you can solve a much simpler classical mechanics problem. Okay, so for that, let us start with this equation again. And you see that if I have I less than IC, then you will always have a stationary solution. If I is less than IC, then the stationary solution will be given by sine gamma equal to I by IC. And then you don't need these two terms. So this is what I call a stationary solution. But if I have I greater than IC, then of course you know that sine gamma cannot be larger than 1. So the other two terms have to be there. So therefore I don't have any, so there is no stationary solution which means that gamma will vary with time and if gamma varies with time, you know from the Josephson relation that you will have a voltage that will appear and that is of course the definition of critical current. But what we want to know is now we want to actually know the IV characteristic of the junction for I greater than IC. Now, there is a conceptual thing that you have to appreciate. Normally, when we talk about critical current, you go above the critical current. Let's say you have taken a thin wire. You go above the critical current and you are in the normal state. So therefore, your IV characteristics will be linear. What's the big deal in that? In this case, this is not the case because when you are reaching the critical current, remember, you have just reached the critical current of the junction. You have not reached the critical current of the pads. The pads are still superconducting and they are influencing the junction. So the only thing that you are doing, you are having, let's say, continuous evolution of the phase, which means the phase is keeping on twisting in the junction area. It's an effect which is related to superconductivity. It's not the normal state. Okay. So now let me map the Josephson junction problem to the tilted version. So assume that you have a mass. I have a mass and the value of the mass is h cross by 2e square into c. So a mass of this value is moving in the gamma direction, which means that whatever was x in classical mechanics, here the variable is gamma. So that means that in this hypothetical mapping, I have this mass m moving in the gamma direction. And it is experiencing a potential. That potential is u gamma, which is minus h cross by twice e into IC cos gamma. So this is the washboard potential. Okay. So we'll see that this classical mechanics problem will give me the same equation. So, but this is the washboard potential. This is the undulation that you have on the surface. Now I told you that I will be tilting also the potential. So the tilt term is here. This is the tilt of the potential. So the larger the current, the larger the tilt. And on this washboard I
Sir,
have four.
sir, will you explain the potential again? How this is can be realized?
Explain the potential means the potential is written. What do I explain here?
Yeah, how this comes from the watchboard potential? Because if a mass moving in the gamma direction, how this can be a potential? That's all.
Okay, wait. I am giving you the mass. I am giving you the potential. I am giving you the viscosity. And then you remember Newton's law, I hope.
Yeah, that's not my issue. I am because then I'll say that it will be a choice, and then I'll see that what will the equation of motion is satisfied or not.
Of course, it's a mapping. This is called mapping. It is a problem from which I will be able to use my intuition and get certain properties that otherwise, see, ultimately, if you want, you can take the differential equation, put the differential equation on a computer, and if you are very good at programming, you can just brute force solve the differential equation. Then you don't need to do any such things. But
Okay.
if you want to get a physical intuition of how things will behave, then this mapping will help you find that out.
Okay. Okay. Got it.
Okay, and on the washboard, there is a viscous potential, there is a viscous drag. And that viscous drag is given by this quantity here. You know that viscous drag is proportional to velocity. All right. So if this is my potential here, then from this I can of course calculate the force, which is minus del u del gamma, which will be minus oh, okay. This quantity has the units of energy, and I will call it EJ. Yeah. Okay. And plus H plus I by 2E. So this is the force. Now I can apply Newton's law. So the mass is H cross by 2E squared. C d square m dt square, that is equal to minus ej sin gamma plus h cross I by 2e minus h cross by 2e whole square 1 by r d gamma dt, and this is the original Josephson junction equation. So this is the RCSJ equation, but what I have been able to do is that I have been able to map it exactly to a tilted washboard model. Okay, now let's take the tilted washboard. So we will see immediately why the tilted washboard is interesting. So let me draw the potential. I have the potential which is like this when I equal to 0. So the potential I equal to 0, the potential is given by, actually I think it should start with a minima. Anyway, it doesn't matter, but just for. So in this case, the potential U of gamma is minus Ej cos of gamma. Okay. Now, the moment I apply a current, suppose my phase is here. Okay. So this is, I can take my 0 anywhere. So this is 2 pi. This is 4 pi, 6 pi, and so on. Now, it doesn't matter where the phase is, as long as the phase is not changing as a function of time, I will have no voltage that appears, the current will freely flow. Now, I apply a current. So, what will happen when I apply a current? When I apply a current, there will be a slope like this. And this potential now is given by this. So this particle, even then, when I apply a current, it will not move. Till what point? So till the point when the slope here means when this maxima will disappear, so that means the slope essentially the du d gamma has to be 0. Oops, sorry. And this, when this happens, when the du d gamma becomes 0, that is exactly the point where you have, so sine gamma, which is I by IC. So you have a minimum as long as you have this condition which is satisfied. Now when I is greater than IC, now what will happen? Okay, let me not draw this axis all the time. Now I have put the slope so much that this I have lost any minima or maxima. So this is the particle will now start rolling down this surface. All right. So this particle will roll on this surface, and if I had no viscosity, then it would keep on accelerating, which means the voltage would keep on increasing and it would become normal. But I have a viscosity, if you remember. So therefore, if I have a viscosity, then there is a terminal velocity as well. Therefore, now we will consider different situation. And the first situation we will consider is under damped junction. So in the case of this under damped junction is when the junction has Q which is large, and Q is large means R, so essentially RC has to be large. Because remember, Q was omega p RC. All right, particularly the capacitance, it has to be large here. So what would be the terminal velocity? The terminal velocity is when the system is no longer accelerating, the particle is no longer accelerating. So therefore, the second derivative term can be neglected, or rather it's not neglected, it is 0. So I have hc by 2e sorry, H cut IC by 2A is given by this quantity here. So this is the Josephson relation that I know. So therefore, I will get a voltage which is R into IC abruptly the moment these balls start rolling. So now if I plot, and this will be, it will become obvious why we did the mapping right in the next step. So voltage as a function of current. Initially, I increase my current, ball is not rolling. Ball is not rolling means the gauge invariant phase is time independent because my ball is at a fixed gamma till I reach IC. The moment I reach IC, immediately the ball start rolling, and then it will, I cannot catch the transient easily. I am doing a DC measurement. So it will start rolling and it will go to its terminal velocity. By the time I do the measurement, it will be already at the terminal velocity, which is this voltage here. So I have not drawn it correctly. Let me draw it. So I'll have an abrupt jump and then it will start going linearly. If I extrapolate this back, it will go to 0. Is that clear? Is it clear so far to everyone? Because if it is not clear up to this point, then it will not be clear what I will tell next. Because the next thing is much more interesting. Okay, if everyone has understood, then let me go to the next thing and let me ask this question. This is the current versus voltage curve that I got when I increase the current. What will happen when I decrease the current? Now I am here at this point and I want to decrease the current. How will the current voltage curve look like? And for this, remember that we have mapped the problem into a tilted washboard, a particle moving on a tilted washboard. So think in terms of a particle on a tilted washboard and tell me what will happen when I decrease the current. Yes.
It will goes like as a I mean as you drawn the extrapolated line. I mean this
Why? Why?
uh, uh, because when I decrease the current, that's mean I actually uh, 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 when I decrease the current at first, when I is greater than IC, then it will I mean regain its shape, and after that it will retilt. I mean it will again getting flattened. I mean if this whiteboard model according to this.
Exactly. So when I am reducing the current, I am again making it flatter.
Yes, yes.
I am
It
reducing
is,
the slope.
yes, yes.
Okay.
Uh,
So then, why should it go according to as per the dotted line?
uh, uh, because these balls for this case, these balls already have a momentum type of things. So
Very
so it
good.
have an extra inertia.
Very
But
good. You are
so that's why,
absolutely correct. This ball already has a kinetic energy.
yes, yes.
Okay, that's right. And then now continue the argument.
And for this, when this I less than IC, then it will not abruptly jump this potential, I mean voltage to zero because of its kinetic energy. This voltage will goes to zero when this surface again goes to its flat. I mean when this is absolutely flat, then it will voltage will goes to zero.
Okay, your argument, you have got the essential thing, but your argument is not entirely correct. Let me now explain and give the real argument. By the way, who was asking why we are doing this mapping? Was it Amit?
Yes, sir. Yes, sir.
Okay, so you'll see why we are doing the mapping. And then your job is to get the same answer for me without doing the mapping. That will be your special assignment. Okay, so now we are reducing the current. When I am reducing the current, I am making it flatter. But as Gurachand is explaining us, the particle already has a lot of kinetic energy, which is given by the terminal velocity, half mv square, where v is the terminal velocity. So therefore now when I am making it flatter, the potential wells will reappear. But the particle has enough kinetic energy so it can go over the potential well. It doesn't need to stop. When will it stop? It will stop only. Now the point is that remember that if I did not have any damping, if I did not have any viscosity, it would never stop. Because it has this kinetic energy, it will just keep on going. What will happen is that because there is this damping, at one point you will reduce enough of the kinetic energy in one cycle that it will not be able to cross the barrier anymore. And at that point, the particle will stop. But that will have, for that, you will have to tilt it back a lot more than you had originally tilted to make it move. So therefore, you will get a hysteresis. Depending on the damping, you will have a hysteresis. So an underdamped Josephson junction, the defining characteristic of this is a hysteresis in the IV characteristics. All right. Now, how much is, so this is the critical current. We know how the critical current, we have calculated the critical current in terms of the superconducting parameters. Now, what is this current? This is what is called the retrapping current. At this current, I am trapping back the particle. And this retrapping current, you can calculate by actually doing a calculation of the energy loss because of viscosity in one cycle. And that has to be large enough so that the kinetic energy from the kinetic energy that you had at the terminal velocity, it should reduce enough so that it cannot cross the potential barrier anymore. This will be an assignment problem in the next assignment because today I have already given you one assignment. but since I am giving you in advance, you can as well do it. Show that the retrapping current under this simple approximation is the critical current divided by pi into the quality factor. The quality factor actually is related to the dissipation, and that's how this quality factor comes in. So this is an approximate relation, but it's a good relation. And this is what I want you to calculate. So Amit, are you now convinced on why we did this mapping? Can you explain to me these hysteresis without doing the mapping, just looking at the differential equation?
Hello, sir. Are you saying something?
Okay, so what I want you to do, Amit, is this. Take this differential equation, go to Mathematica.
Yeah, yeah.
Solve it on Mathematica and show that it has bistable solutions.
Okay, okay.
Okay? When you increase I, it will have one set of solution. When you decrease I, you will have another set of solution. Of course, when you solve it when you solve the differential equation numerically, you will get these two solutions corresponding to differential initial condition that you put. But try to solve this and it will be fun to do it. All
Okay,
right.
sir.
So let me log off and we'll continue on Monday. By the way, are you all working on your video projects? So shall
S-
we? Yeah.
so, sir, it would be better if I can discuss with you about the project in the next week for a few minutes.
What was your project? Tell me again.
And reflection and its application in spectroscopy.
Okay, that's a very straightforward project. Uh, Surajit, can you spend some time tomorrow during the tutorial hour with Amit? Okay,
It would be difficult if can it can be organized in the next week. It would be easier for me
you have an
because I
exam
have
or
no, I have not gone through all the materials thoroughly. That's why.
okay, so in the next week you coordinate with Surajit and based on his convenience you fix some time and discuss. After that,
Okay.
if you have any further clarification, I can sit with you.
Okay, sir. Thank you, sir.
All right. What about the others? Because now we have to fix some time scale. And I would say that all these videos should be in the first week of, at least in the first week of January. We cannot go beyond that. All right. So all of you keep working on it. If you have any difficulty, get back, but don't keep it till the last week. You will be doing a really bad job. And since we have decided that the entire midterm marks is based on this, there is a significant component that the marks will come here. Because this in the online mode, and particularly for an advanced course like this, I don't think that the exam is very useful. So we will not have too much of weightage on the exam. Most of the weightage will come from the assignment and these video projects, which will carry of the order of 50% of the weightage. All right. So see you on Monday.